next term. I would like to now speak about the Goiânia incident, and we do have about 4 students absent. So I'm screen capturing this so that they might be able to follow along. Now, you don't need to get your booklets out, just have a look at... This is a story. Guys, if you want to go outside and chat about it, you can. Leave the classroom, talk about it, and then come back in. Remember I said, the physiological effects of radiation on humans, you cannot just do it in a clinical trial. You can only really look at accidents, chemicals, nuclear incidences, explosions, spills, leakages, things like that. And this is one it's not that famous, but there's a lot of stuff going on to this story. So I've taken most of this info from Wikipedia. This was a contamination that occurred back in Goiânia in Brazil. Now, there was a radiotherapy source stolen from an abandoned hospital site. Long story short, it was handled by a lot of people, and it killed 4 of them, and many other people had significant poisoning as a result. Now, what it was a 93-gram pellet of cesium-137. That's the same stuff that was sitting in your little cows in yesterday's lesson. Cesium-137, I'm pretty sure, because then we went to barium-137. But its activity was way more than what we have in the classroom. It was encased in a canister made of lead and steel, and it was a wheel type, where the wheel rotates to reveal an aperture that would then send out a beam of gamma rays. Ready? Gamma rays. Alright, so obviously you can slide your shielding away, and there's a window here. This was used to treat cancers and tumours. So they collimate this beam of gamma rays through shielding, and then you place, the lump of tumorous tissue in front of this beam. So people would come in for treatment to bombard their tumour with high amounts of gamma rays. Okay? Why did it go back to the top? That's a pain in the butt. Scroll, 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 zoom. Okay. There you go. Now, here's the thing. The activity of the source in 1971 was 74 terabecquerels. The atomic energy, that's how they described it. The pure substance would be 814 terabecquerels per kilogram. There was 93 grams, so just less than a tenth of a kilo. So there's your activity. Half-life of about 31 years. Okay, so by the time it got around to 1987, it hadn't yet gone through half of a half-life. So the activity at the time was quite high. So there we are. Look, I could do a comprehension question in an exam. You'd have to figure out A naught half to the power of n. 50.9 when it was stolen. The dose rate at 1 metre from the source was 4.5 gray per hour. Now it's gamma ray, right? That's got a quality factor of 1. So if you were a metre from this beam, over an hour, it would give 4.56 sieverts. Not whole body, but localized. Remember, you're targeting a tumour. So if you were to give that to a localized section of tissue, it's going to be a lot of damage to that region. So in Goiânia at the time, there was a lot of poverty, lots of businesses and government agencies going under. The abandoned site. President, what would happen with this? Or what would happen to the cesium bomb? Security guard protected the abandoned places. The owners of the hospital trying to say, look, there's some dangerous stuff in there at the abandoned site. Now, the theft of the source. So now Roberto dos Santos Alves and Wagner Mota Pereira illegally entered. They're looking for scrap metal, okay? So they're going into abandoned places looking for lots of iron and lead and zinc and copper that you could rip apart, and then you could take it to a scrap metal and sell it for scrap, okay? So they found this, they partially dismantled it. They thought it would have some scrap value. They took it home in a wheelbarrow where they began dismantling it. Then they began to vomit, diarrhea and dizziness, and his left hand began to swell. The burn on his hand was the same size and shape as the aperture, the opening where the gamma beam comes out. Eventually required amputation thereafter. Now, inside, he was puncturing the aperture's window with a screwdriver, and he saw this deep blue light coming from a tiny opening. He inserted the screwdriver and brought out these little glowing powder, scooped some out, thinking it was some kind of gunpowder. He tried to light it, but no mas. I believe that's Spanish, I don't know. It would not ignite. They thought it might be some kind of ionized air glow or Cherenkov radiation. If there's water or moisture in the source, something really cool can happen. Cherenkov radiation is a glow that's emitted when particles are travelling faster than the speed of light. No, everyone believe me just that. It isn't in a vacuum, but in water, light travels 50% slower. Light travels at 2 times 10 to the 8. So if you have a beta particle that travels out faster than 2 by 10 to the 8, which is possible, technically it's travelling faster than the speed of light in its medium, and you get this kind of sonic boom of electromagnetic radiation. That sonic boom, similar to sound, breaking the sound barrier in pressure waves, that sonic boom is released in the form of light. So what you're seeing here, this blue glowing light, are beta particles that are travelling faster than the speed of light in water. Okay, so that is possible. If you took that out of the water, you're not going to see that effect because nothing can travel faster than 3 by 10 to the 8, but it can travel faster than 2. So, brought the item to a nearby scrapyard. De Ver Ferreira, the owner of the scrapyard, noticed this. Thinking that the capsule's contents were valuable or supernatural, he immediately brought it into his house. That was probably silly. Then he invited his friends and family to come over and view it. Again, not a good idea. They managed to get some rice-sized grains of glowing material from the capsule. They again sharing it with the family and friends. That same day, Gabriella fell ill. Then it was sold to a second scrapyard. So the government, when they came to clean this up, they're just like literally going into crisis mode, trying to figure out where everything was to try and contain. Ivo and his daughter. 6-year-old daughter ate a sandwich. She was fascinated by the blue glow. She applied it to her body and danced around because it was this glowing blue paint. That was not good. Dust fell onto the sandwich which she was consuming. She eventually absorbed 1 gigabecquerels, receiving a total dose of 6 sieverts, more than a fatal dose. Now, Gabriella, she was the first lady who noticed everyone's falling ill and vomiting. They thought that it might have been food poisoning. Maybe it was some bad... No, I'm going to be inappropriate. Bad food. I'm trying to think of a Spanish meal. She reclaimed the material. She thought, all right, this material might be dangerous. Best to put it in a plastic bag. Which, it kept the contamination low, but obviously it's not going to shield you from beta particles. So she took the bus. Where is it? She reclaimed it, transported it to the hospital, kept in a plastic bag. It's detected that morning by a medical physicist who used a scintillation counter, similar to our Geiger counters. The thing was going off the charts. Holy crap, call 000, let's get this sorted with. So eventually, over the time, 20 people showed signs of radiation sickness and required treatment. There was a little bit of mass hysteria because people then swarmed to the local hospital. They actually may have had food poisoning, but they thought that they may have been contaminated. So all the hospitals got flooded with hundreds, tens of thousands of people. But of those, 250 were actually suffering from radiation poisoning. The others, well, they were just sent home. So, here are the fatalities listed in greys. But remember, beta particles, sorry, gamma rays, my apologies, gamma rays, quality factor of 1. Again, if it was ingested, so the sandwich, right? The sandwich, you eat the sandwich, it gets into your stomach. Well, that's going to irradiate all of the regions of your intestines and your stomach and your bowel. If you are just standing in the room with the girl that's dancing, you're going to get a full exposure, okay? If the girl that's thrown it all over her body and is down, that's also going to be a full exposure. The bloke that had his hand over the aperture, which later required amputation, that wasn't a whole body exposure, that was just a localized exposure, okay? So it varies. So poor Liede she received 6 sieverts. Again, these are approximations. How much did she come into contact to? Where on her body? For how long was she in contact with it? So these are just estimates. So she passed away October 23rd. So let's just quickly go back, because September 13th, right? That's when the source, September 15th and 16th. So mid-September, that's when the contamination started to occur. Gabriella, poor lady, she was the one that kind of saved the day. She received 5.7. Israel received 4.5. Alves de Souza got 5.3. De Ver, okay, so this bloke received nearly 7, but he didn't die from the radiation poisoning. He became an alcoholic and got cirrhosis of the liver. So basically, from depression and drinking, he ended up losing his life. Okay, so here's our bar chart. So again, when you look at that LD 50/50, if you get above 5 sieverts, it's pretty serious, 50% chance that you're going to die, even though that bloke got 7 and managed to survive. So he may have been healthy, strong immune system. His body was able to try and repair all the damage. But obviously the younger children, they're not going to have as strong an immune system. Yes, Scott?
You said earlier that gamma rays were equal to 1 or something like that.
And beta?
Yeah, and beta. Does that mean, because if you got 6 sieverts, is that 6?
So remember, your dose equivalent is your absorbed dose times the quality factor.
Okay.
And we're going to say gamma rays quality factor of 1. All right, that's the lowest, and then you compare the rest. All of the others are going to do more damage. That's why their factor is larger than 1. Remember what we said, that beta particles, it depends on the energies of emission. So if I go back to the Guyana incident, if I just bring up cesium-137, see guys, any radioisotope, you can have a look. The physical properties on the right-hand side, 30.1 years, decays via 50% beta, and then 6.6, well, why is that 0.6? That doesn't add up. This is a bit of a, is it energy? Oh, sorry, energies. Okay. So, this is getting a little bit tricky, but we try and tell you that an isotope will do just this, and you have to draw the nuclear decay. But sometimes there are multiple modes. So what we're saying is it could decay to a beta stable barium by emitting a beta particle of that to get it there. Then the barium is unstable and emits it. Well, hey, that's what we were measuring in yesterday's lesson. This was happening in the generator, right? In the generator, and we tried to shield it with the metal generator housing. This was happening in the planchette. But occasionally, it might just go straight from there to there. This will only occur, remember, if the nucleus is still in an unstable orientation. Sometimes when the beta particle is emitted, the remaining daughter nucleus is stable. But have a look. there's this wonderful law in physics called conservation of energy. So if you looked at the two different processes, that value plus that value would add up to that value. Everything's conserved. Okay? So it can either go beta than gamma or just straight beta. Okay? So those are the two different decay modes. It should, I would hope, to 3 significant figures. So there's your energies, 0.6 MeVs and 0.5 MeVs. Let's go back to the cleanup. So you can read this. The topsoil had to be removed, houses were demolished. Basically, your particles are so small that you can't just go in with a broom and a dustpan. You have to literally just remove the entire soil. Then where do you put the soil? You've got to put it into plastic bags, and then it's got to be placed somewhere for 10 half-lives. How long's 10 half-lives? 300 years. In 10 half-lives, we're going to go, let's just do some quick mathematicals. 51 terabecquerels. A tera is 10 to the 12 becquerels. Half to the power of 5. Oh, by the way, some was actually reclaimed, so it's the activity... Anyway, let's just figure that out for us. This pellet that was sitting in an abandoned hospital, in 300 years, could somebody tell me what the activity is? Oh, sorry, it's in the power of 10. My bad. Power of 10.
4.9
That's still 49 gigabecquerels. That's huge. That's a G. That's a 9. That's still a huge amount. So that's the problem. When these radioisotopes are made, you go thinking, great, this is in the next 20 years, we're going to use it in this hospital, but what about the next 280 years? What are we going to do with this? And this is the big question about nuclear waste and the products of fission and fusion and alpha and beta, and even the sources themselves. This was just an unfortunate bunch of Brazilians. What if someone came in and actually stole that because they wanted to use it for nasty purposes? Run around throwing it all over the place, okay? So it's important things to consider. However, let's go to... Oh, for God's sake. Scroll. Oh, this... My laptop can't... Okay, now, gentlemen, at the back there, have a look. I'm just reading through the booklet. We're going to spend probably about a lesson's worth discussing therapeutic uses. So, using radioisotopes to detect cancerous tissue or tumours or things that might be going wrong in the body, as well as treating it. So you can split this radiotherapy into detection and then treatment. Okay? So radiotherapy. Further cell damage. We can concentrate your radiation to your cancerous tissue by a number of techniques. So the first one is your gamma knife. If you can get a beam of radiation that can pass through and have a common focal point being the tumour, then the majority of the dose is going to be localised to the tumour. So for example, if you have a tumour there, you place yourself on the bed, and then you get this device that basically sends out a beam of gamma rays. Okay? Now, all the way through your person, all of the tissue in that line is going to receive the same amount of dose, whether it's healthy tissue or bad tissue. But if we can rotate this beam around such that it is always pointing at that point where the tumour is, then it's going to minimise the dose that healthy tissue gets. Meanwhile, if the focal point is the tumour, then it's going to be cooked. Okay? And so people would come in, they've obviously first off, they've found out where the tumour is. It's right there, it's this big, it's this kind of tissue, it's got this kind of malignancy, or how dangerous it is. We know the size, we know the mass, and we know where it is. All right, so they put you in, and they put you in often a kind of a map across you, so that they can make sure that they're targeting the right point, and then you just lie there. This is what would happen if you went into that hospital in Guyana. In there would be some cesium-137, the window would open and the gamma beam would come out and you would irradiate your tissue. And it would slowly rotate around these sweeping three-dimensional axes, underneath, around, sideways. You get the idea. You know, all different directions, always focusing at that point. Okay? Then you can insert chemically inert, so you don't want chemical reactions going on, radioactive implants. Now, this is sometimes called brachytherapy. Hang on, let me try that again. Or, oh gosh, what was it called? TAT? Targeted alpha treatment. TAT. So, if you know where your tumour is, it's about yay big, this volume, and it's located here, you can literally implant a pellet of radioactive material, and the radiation is emitted in that region. Now, it would only be alpha, because if it was beta, it would then travel out of the tumour and it would start to irradiate healthy tissue. It definitely cannot be gamma. So this is called targeted alpha treatment, if you wish to know what that acronym means. Now, normally, if you Google image search brachytherapy, you've got to be careful because prostate cancer is often treated this way, and breast cancer as well. So I don't want any nasty or gruesome images coming up on Google image search. But sometimes you can see x-rays of the brachy pellets, and sometimes for prostate treatment, nasty, you can insert 20 pellets into the prostate tumour, all requiring, a separate catheter or syringe to inject a pellet and leave it there. All right. Obviously, local anaesthetic would occur, but a person could be walking around with these pellets in them for a week, a month, 3 or 4 months. Okay. So you allow the radiation to do its damage, then you have them removed. Okay. Now, what I want you to consider, and you might need to consider this in tests or exams, is depending on the type of treatment, you either need it to be alpha, beta, gamma, and you either want it to have a long half-life or a short half-life. So, for example, your gamma beam, that's gamma, and generally we want it to be a long half-life. Okay? Have a think. The long half-life means that it's going to sit in that machine and not need replacing. If it's got a half-life of 10 days, then every 10 days you've got to remove your cesium-137 and get some new cesium. But because it's 30.7 years, 30.17 years, it can sit in that machine for decades. The intensity of the beam will slowly decrease, but you don't have to replace it. It has to be gamma, because we need it to actually penetrate the body and get to the tumour that might be somewhere inside your torso. For brachytherapy, it needs to be alpha. So it's alpha and short or mid-term half-life. As I said, these pellets might be inserted into the tumour and they might stay there for a month or 2 months or 3 months. So a half-life of 60 seconds, like barium-137M, isn't going to work, because after 600 seconds it's gone. But if it's got a half-life of a couple of months, then it's going to remain effective while this person is going about their day-to-day lives. Okay? Next, radiopharmaceuticals. Now this is a really cool thing. And I'm going to basically explain it by drawing a molecule. So here is a molecule. Wouldn't you know it? I'm going to make it a little bit complicated molecule with various colours. Okay, now here is a molecule. It might be a molecule that our body is used to taking in. Maybe our liver needs this molecule, maybe our brain, maybe our thyroid, maybe one of the glands in the back of our throat, maybe it's taken in our lungs or our stomach or the muscles, all right? So depending on the molecule, it's going to be taken in certain organs. Now, if we know the molecule, that's one part of the battle. What we could then do is replace one of these molecules with a radiopharmaceutical, with a radioisotope. Okay? So we're going to take that atom out and replace it with one that's radioactive and eventually would emit that in the form of alpha, beta, or gamma. Then you could inject that into the body. It would travel through your body, but a certain organ might be taking that molecule in because it needs it. Okay? And then it sits inside that organ, and then that organ is going to receive a certain dose. So, for example, thyroid cancer, thyroid's taking iodine. Iodine is an essential mineral that you get in your diet. And if you inject iodine into your body, it's all basically going to get taken in by the thyroid, which is just in the base of your throat. Right? Like a filter, it just grabs all the iodine. No other part of the body wants iodine except for your thyroid, because then your thyroid uses that to make hormones that can then travel around the body and send messages. Okay? So, that's a really good one. But I want to quickly talk about where the rest of my screen went. All right, just under here, could we please write, and I'm just going to flip my laptop, and okay, now, oh, there we go. Okay, what am I going to write? I'm going to write, we said it was either treatment or detection. So I'm going to write detection. So those are the three kinds of ways that we can attack a tumour, with a gamma beam or brachytherapy or a radiopharmaceutical that might be able to be taken in by that tumour. Okay? But let's go back to, we should have started with detection. Let's say you're not feeling very well, something's not right, you go to your doctors, you have your blood tests, everything's normal. Okay, we're still trying to figure out, we're trying to diagnose. So we could probably write the word diagnostic. So you're trying to diagnose, that means you're trying to determine what is wrong, trying to find out what's wrong. Okay? So maybe the doctor says, well, it's coming from your pancreas, and so we're going to inject you with a radiopharmaceutical that is going to be taken in by the pancreas. Okay? So could you please write? A radioisotope is placed in a certain molecule and acts as a tracer, meaning it can be traced through the body. So suppose we say that there's something wrong maybe with your pancreas. Okay? Your organ, your pancreas has to do a certain function, and apparently it's not working. So what they do, they try and find a molecule that is going to be taken in the pancreas, and there's probably going to be a lot of them. That's half the battle. Then they have to find some way to put a radioisotope into that molecule. It then becomes a radiopharmaceutical. Right? So we inject that into the body with a big ass syringe, and then it travels around in your bloodstream. Okay? And then as your blood passes through the pancreas, that's when your pancreas says, oh, thank you very much, I'm going to take that molecule, I need it, thank you, thank you, thank you. Then, here's the deal. That's going to be emitting radiation. Okay? So all we need to do is take a camera of the pancreas to detect that radiation. So literally, when you are injected with your tracer, you wait around for a few hours so that it can, or you might need to come back the next day, so that it can be absorbed by the required organ. Okay? Then you go and you lie down, and if this is emitting, say, gamma rays, then obviously this would be a gamma camera. Okay? And if we know the energy of the gamma ray, we can literally tune our gamma ray to detect that energy. As we said, the barium-137M was emitting 0.611 MeV. So I could then tune my gamma camera to 0.611 MeV. And you sit there and it counts all the photons. Now, your pancreas, let's suppose you can get two images, really. If your pancreas is working fine and it's taking in the radiopharmaceutical, it will emit the gamma photons. But there might be a region that isn't. You'll get this dark spot. And so that is our abnormal tissue. So you're looking for like a contrast image. You're saying, where am I getting the gamma photons from? And where am I not? You get a dark spot. That dark spot might be the tumour. Okay? And so again, it's not just like a normal picture. It's going to be a three-dimensional picture that they take slices of, and then they can generate three-dimensional images called topographical images, like MRIs. Or it could be the opposite. Maybe the tumour takes in the radiopharmaceuticals, in which case your pancreas would be the dark spot, and then you get this big hot spot. And that may be, hang on, I'm going to go back to yellow. That may be the abnormal tissue. Either way, it's a contrast. You're looking for the difference between healthy and unhealthy. Okay? Now, I just picked pancreas, and they, your radiologist would have a huge list of molecules and a huge list of traces that they could use. What I've placed a little table underneath dosimetry in our nuclear tab. This is just a short list of all the different traces that can be used. Okay? So, bismuth, it can be used for targeted alpha therapy. Okay, alpha, half-life of 46 minutes. Okay, cool. That's a very short-ranged half-life. Cesium-131 can be used for brachy. It emits soft X-rays, soft and hard. That refers to the energy that they have, so low-energy X-rays. Let's go down to one really, really important one. Technetium-99M. This is such a beast of a radioisotope. Okay? Technetium-99M is such a useful atom, it's really, really easy to place onto many different molecules. Right? And so it's very easy to make a radiopharmaceutical with technetium-99m. So there's a number of reasons. It's easy to produce. It can be placed onto many different molecules. And so then you can use it to detect in brain, thyroid, lungs, liver, spleen, kidney, gallbladder, bone marrow, salivary glands, heart, blood pool, infections. Okay? Most commonly used in diagnosis, and 80% of all scans use technetium-99m. It's in your body because it has a half-life of 6 hours. So you get your injection, you come back a few hours later, you take your photo to try and detect the cancer in the certain region. After 10 half-lives, 60 hours, just under 3 days. Under 3 days, that activity has disappeared. Many people that are given technetium are told that basically don't sleep with your loved ones for a couple of days, don't handle young infants or newborns, because for 2.5 days you are emitting gamma or beta rays. Okay? So it's a pretty cool story. So these are just all the different... Okay, and there's heaps. I found a website that has all these different atoms. And that's as far as I know. Then you say the word chemistry and you go, oh yeah, okay, put it in a molecule, then put it in your body. I don't know how they actually do that. I'm sure it would be a very difficult process of taking that radioisotope and sticking it into a molecule. Okay? So I'll stop talking there, but that's just a nice list of different radioisotope traces. And I'll see you guys tomorrow or Friday? Tomorrow.